finish him. Kill the guy now. You have to come.
What? What is this?
Good day, sir.
You are watching Jakepan in my house.
No, it's King Kong, sir.
King Kong. You've never heard of ACTV before in your life? ACTV is very educative, informative, and there are football sports there. There is entertainment. There are a lot of things you can even attend lectures here. All you know is watch all those nonsense artists and do nonsense, or you watch nonsense on TV. Last night you almost came in bed with your fist.
It's not me, sir.
And you wake up every morning, the bed will be so rough, like you've been fighting kung fu in your dream. That's the reason why you have F's in your courses, like especially made for you.
I have it last semester.
We by pounds on you. Very stupid. We are changing that section to ACTV right now. And oh God, the baby wants to have the first born. Stupid boy.
Hello class, I welcome you to today's class. In previous classes we've treated some basic concepts in topology. Today we are continuing from where we stopped, and we are going to something which has wide application in topology. Already we've dealt and we have dwelt on the elementary definition of topology. We've looked at open sets, closed sets. We've also looked at limit points, also known as accumulation or cluster points. We've also considered in our previous classes the concept of continuity when is a set said to be continuous. We've also looked at the concept of derived sets. And today, we want to look at something which is almost available in almost every concept of algebra, which is equivalence. We are looking at the concept of equivalence of topologies this morning. Of course, you realize that when we are talking about equivalence of topologies, you note that topologies are sets of points, and also they are also a family of sets. And so we need to look at it from the structure of sets, first of all, and then we'll now bring that equivalence into the concept of topology. Now you know that in algebra, when you define equivalence of sets, you consider the cardinality, the number of elements in a set. Of course, we know a set A is equivalent to a set B if and only if the cardinality, otherwise known as the number of elements in A, is equals to number of elements in B. Not necessary that all the elements in A must be in B and all the elements of B must be in A. No. But when we talk about equivalence of sets here, equivalence of sets, we are dwelling on the cardinality. As we can see also, you can also have a situation where a set is being operated or is closed in terms of binary operations. For instance, let G be a set, or let me call it G1, or let me define it as group here. So equivalence, when it has to do with set, you dwell on a cardinality. But when you are now dealing with a a group, let's say this is a group with its operator O, and then you also have another group with operator star. Okay? When you are defining equivalence of a group, for instance, this equivalence has a name which we call isomorphism. Now, you look at an isomorphism if you can have a map that takes an element from here to here, okay, that will not alter the two operations. So you have what we call an isomorphism. And when you write it, you want to write an isomorphism, you denote it this way. G1 is isomorphic to G2. So when you are dwelling, we call this isomorphism. When you are dwelling on group, then you can have the third aspect of equivalence, which is what we are looking at today, the equivalence of a topology. So if you have two topological spaces, let X and Y be topological spaces. Of course, you know when I write X, it doesn't just mean X, it can mean X with its topology on it, and it means Y with its topology on it. So we say that equivalence of any two topological spaces, for it to exist, there must be a map. So you say, let F be a map from this topological space to another topological space, Y, such that not just a map, is a bijective map, such that F, that is the map, and its inverse, this, are continuous. Now, when you have the continuity of both F and its inverse, of course, you know the inverse of this map will take Y to X. So that is the inverse. And that inverse is what we have here. So if both of them are continuous, then we say then X and Y are said to be homeomorphic to each other. The term homeomorphic is what we call the topological equivalence. Topological equivalence. This will soon illustrate by examples. So, for a set to be equivalent, we say the number of elements in both sets must be equal. Okay? But when you are dwelling on topology, you are not just dwelling on the set, but you are also dwelling on the topologies that are defined on those sets. Of course, you know that these topologies, as earlier said, are subsets of the power sets of the set X on which they are defined. So that is it. So for sets, we say set equivalence. For groups, we call the equivalence isomorphism. Then for topological spaces, we call it a homeomorphism. Homeomorphism. Okay, so it's called homeomorphism. The word morphism, this morphism here arises from the word map. So whenever you hear morphism, it's simply a map. So that it is an homeomorphism. The word homeo here means you have both the continuity of the map and its inverse, okay, established on the map. So when you have that, you have what we call an homeomorphism. Now let me make some other definition. A map F is bicontinuous or topological if it is open and continuous. If it is open and continuous. And these definitions are very necessary for what we are about to do next when we are discussing on the equivalence of topologies. So, a map F, okay, is bicontinuous. Bicontinuous or topological if it is open and continuous. When do you say a map is open? You say a map is open if it maps an open set to an open set. Okay? If it maps an open set to an open set. Okay? You can say that this U here belongs to the topology of X, and this V here belongs to the topology of Y. So, if it is open, then the continuity means that if this is V, this V can be written as F acting on a U. So by the continuity of it, it means that if it is open, U is here, and V is here. We can also say that the inverse of F on V belong to X, where V belongs to Y. When this happens, we have what we call bicontinuity or topological nature of a map. Now, we can also make the claim that a map F which takes X to Y, just like the one there, is an homeomorphism if it is both bicontinuous and bijective. If it is both bicontinuous and bijective. So this same map here, the map F which takes x to y, is an homeomorphism if it is both bicontinuous and bijective. So this is an alternative definition of homeomorphism. So you cannot talk about an equivalence of topologies without talking about a map which is an homeomorphism that exists between the two topological spaces. Let's look at a typical example. Okay. Now, let X be a set comprising of points A, B, C, D, E, and Y be another set comprising of G, H, I, J, K, with, this is an example, with their respective topologies, okay, given by to X. Of course, every topology on X must contain the empty set as well as X. And then here we have C, we have CD, and then we have A, C, D, and then B, C, D, E. Okay? That's a topology. And then we have another topology on Y. Of course, Y also, topology on Y must contain an empty set as well as Y. And then we have I, we have IJ, then G, IJ, then H, I, J, K. Okay, this is the topology defined on X and Y. You will see the map. If you want to establish a map that exists between X and Y, let's assume that is the map. So here, it will map an empty set to an empty set. Okay? That is trivially true. If you have a map F, which must be an homeomorphism between X and Y, it will take X to Y by that definition. Now let's look closely. What is the third element or the third point inside this set? C. Okay? And then the third set in here is what? I. And so, if you want to look at the element here is C, and the one directly opposite it here in Y, in terms of Y is also I. If you look at CD, you also have IJ, CD, IJ. You have ACD, you have GIJ. corresponding. And then you have B, C, D, E. Then the last 4 here is H, I, J, K. H, I, J, K. So there is a one-to-one correspondence between everything you have in both sets. Therefore, there exists an homeomorphism between the two. In other words, this is what I mean. F is a map that takes X to Y. Of course, it will also take an empty set to an empty set. Now, here, F takes A to G. It takes B to H. It takes C to I. It takes D to J. And then it takes E to K. So there is a one-to-one map of everything you have in this set with what you have in its mirror set here, codomain. Therefore, we can conclude that F is an homeo. Note, it is not homo. It's not an homomorphism. An homomorphism can exist between two groups. But here we are dealing with homeomorphism. So, homeomorphism. And that means that X is homeomorphic, that is topologically equivalent to Y. So, now we want to see a situation where you have 3 topological spaces. Can there exist an homeomorphism between 3 topological spaces? And can we claim that this relation between topologies is an equivalent relation? Let's take a look. Now you have a theorem here, or let me call it a proposition. A proposition says let X, Y, Z be topological spaces. Then X is homeomorphic to Y. Y is homeomorphic to Z, implies X is homeomorphic to Z. Now, this one is the transitive nature. The transitive nature of homeomorphism. Now you know, before you can claim that an equivalence, that a relation is an equivalent relation, it must be reflexive. So this homeomorphism is an equivalence relation if it is 1, reflexive, symmetric, and 3, transitive. reflexivity, it means that every topological space is a mirror of itself. By symmetry, it means that X is homeomorphic to Y and Y is homeomorphic to X. And then by transitivity, which is this third condition, X is homeomorphic to Y and Y is homeomorphic to Z, implies X is homeomorphic to Z. Now, it is not difficult to prove reflexivity and symmetry. The reason being that you can actually map two sets to each other or two topological spaces that are similar to each other. And you will also see that the map, both the F maps X to X is continuous, and its inverse too also map X to X. So it doesn't change anything. And it's still going to be continuous, bicontinuous, and bijective. And bijective. Similarly, for symmetry, it's not difficult to see that if X maps X to Y and F inverse, we also take where Y to X. Both of them are continuous. Symmetry is already defined. It's already defined because this is continuous and the inverse too is also what? Continuous. It's defined here. This is an homeomorphism between X and Y, and this implies this. Sorry. So this actually implies this. And in fact, they are equivalent. You can go either way. Now, the third one, this is where we have a little work to do. So, we look at a simple proof as X is homeomorphic to Y and Y is homeomorphic to Z. Let F be a map from X to Y and G be a map from Y to Z. Be homeomorphisms. So if you have X being homeomorphic to Y and Y is homeomorphic to Z, then there is a map that relates the two of them. Now we can also see that the composition of this you have, this is X to Y and Y to Z. So F maps X to Y and G maps Y to Z. The composition from X to Z is actually the map of the composition of G and F. So that means the composition of G and F takes X to Z. And this is shown by taking a point in X and mapping it to a point G compose F, which is defined by G of F of X. This is for all X belonging to the topological space X. Now, we want to see that if this is the composition, we want to also see whether the inverse of this composition will be found. Of course, we know for this to be an homeomorphism, their inverse also will exist. That is, the inverse of this exists. It takes y to x. And this also takes z to y. So what do we do to confirm the inverse of this map? Now we want to look at the continuity. Let U belong to tau Z. Be an open set in tau Z. Then, by this, if U is an open open set in tau Z, it means that G inverse of this will take any Z here to Y. So the G inverse takes U to tau Y. Now, and here we see another map here that takes an open set in Y to X. So we take the inverse, F takes an inverse into Y, and when it maps, it will be an open set into X. And from our elementary knowledge of algebra, the inverse of G compose F is equals to when it acts on an open set is equals to F inverse compose G inverse acting on an open set. And of course we see that this is in tau X. So we've been able to establish the existence of a continuous inverse. A continuous inverse of this composition, which is also an open set in X, tau X. By this conclusion, U is in Z, and we have taken this inverse, have taken an open set in tau Z to an open set in tau X. Therefore, X is homeomorphic to Z. That's the end of that proof. So, since we have been able to draw a conclusion that there is this equivalence relation, which we call the homeomorphism of two sets, is reflexive, is symmetric, And lastly, is also transitive. We can make a general conclusion that the homeomorphism is actually an equivalence relation. So with this now, we can define an equivalence class on these sets. And that is what we'll find very useful in the second part of this course. And with this, we've come to the conclusion of the first part of this course, which dwell on the basic concepts of topology. In the next class, we shall be looking at what we call the Euclidean topology. And I believe that you will have a nice time when next we come together. Thank you for listening.